Okay, hello students, this is lesson number 6.5. I would like to prove in this video inverse reciprocal identities where we can always change from cosecant inverse to sine, secant inverse to cosine, and cotangent inverse to cotangent. Tangent. So the only change is if there is any value here, x becomes 1 over x. So the question is why? Last time we have said the inverse trigonometric identities with negative values of x. Among all the six, each of these cases the negative can be pulled out except for the cosine inverse and the secant inverse, where you need to write down pi minus. So in the earlier video on the set one inverse trigonometric identities, I proved this why this is, and this is so easy if you come across, let's say, secant inverse of minus 2. So we can always write this is pi minus secant inverse of 2, which is, that's what we are doing now, secant inverse. We can write it as cosine inverse and makes it easy. So the first one, cosecant inverse of x. Because we don't know, let's assume that we don't know. So let's put it as theta. Then by definition of inverse function, so using the definition of inverse function, that means if cosecant inverse of x is theta, it means this x, let's call it as blue color. So this blue color x, okay, this x equals cosecant of the theta. Then using the reciprocal identities, this x stays the same, and this could be written as 1 over sine of the angle theta. Okay. Then we use the invert handle. This is also we can use here invert handle. And what is invert handle is you are taking reciprocal both sides. So 1 over x becomes 1 over x equals sine of theta. Okay. So which is as good as writing without this denominator 1, and we apply the definition again. Apply and this is back to sine inverse of 1 over, so this x which you see, this will remain the blue color, equals the theta, and then you replace theta. So what is theta is? So this theta is right here, you replace this theta, which is cosecant inverse of x. So we have cosecant inverse of x. So what we did learn is that means if cosecant inverse of x, okay, which is x basically means it is x over 1, so you can change it to sine inverse of 1 over x. A simple example on this example we can take is, if I have a question, what is cosecant inverse of, let's say, 2 over root 3, so you don't have to break your head, what is cosecant inverse, you can directly apply this formula and say, hey, this is nothing but sine inverse, flip this root 3 by 2, and sine of what angle is root 3 by 2, and that is pi by 3, because which is 60 degrees, and sine 60 is, so you can do it a little faster if you use this. Let's go to the second one. Same thing, secant inverse of, if it is x, let's say we don't know whether it is cosine inverse of 1 over x, put it at theta, use the definition of inverse, so this x stays here, the value of x will be here, and this, let's see, it is theta, so this will be secant inverse of, sorry, no secant, definition is secant is this theta. And then use the trigonometric identity to write this equals 1 over cosine of the theta. Then take the reciprocal of on both sides, so this will be 1 over cosine of, okay, which is same as 1 over x. equals cosine theta, and then again use the definition of inverse function, you get cosine inverse of 1 over x equals the theta right here. And this blue color, which is right here, stays there. And then you replace the theta, whatever the theta is secant inverse, that goes right here. You get secant inverse of. So what we did learn is that secant inverse of x is cosine inverse of x. We can take one example on that. So we can take one example on secant inverse is, let's say, secant inverse of root 2. So secant inverse of root 2, the first thing is, hey, can we change it to the cosine inverse? Oh yes, we can change it because this is same as root 2 over 1, which is same as secant inverse of 1. So you do the reciprocal of this, but before that you need to change it to cosine inverse, which is 1 over root 2. Okay, and what is this? Basically is it is the same as root 2 over 2, and cosine of what angle is root 2 over 2? We know it is pi by 4, which is 45 degrees, correct? This is in radians, and that's 45, and done. And the same idea can be used for cotangent inverse of x. Exactly the same way you can check cotangent inverse of x is same as tan inverse of 1 over x. An example will be, let's take one example for this is, if there is a question cotangents of 1 over root 3, let's see. I'm going to make a slight change this to this angle. Let's change this to cotangent inverse of, let's say, minus root 3. Okay. So the first thing is, look at this. If you have cotangent, if there is a negative, you can always write it as minus. So this is that to minus cotangent inverse of root 3. And now you change cot inverse to tan inverse. So this becomes tan inverse 1 over square root of 3. But then, what is 1 over root 3? From the unit circle, if you want to compare, this is root 3 over 3, it's the same thing. And you get tan of what angle is root 3 over 3 is pi by 6, which is minus 30 degrees. We are done. Hope this helps, and we will see. I will make another video. The next video is on solving quite a lot of problems on this, and most of them will be like y sine inverse of sine of. Let's see if I have 2 pi by 3. What is the answer? So the next video I'm making is this one. So basically, many students think that, hey, just cross this out. That's not how it works, 2 pi by 3, because you have to have the domain of inverse. Remember the sine, the domain of restricted domain of sine is should be minus pi by 2, angle to plus pi by 2. So you can't have anything more than pi by 2. So those are the ones that I'm going to do the next video. Okay, hope this helps. As I say, I just like to make these videos to understand how this formula exists. So most of my videos are like, if you like it, please do click on the like button and be in touch continuously to see more videos that I post. Why the identities exist. So the last time I did also was why cosine of A minus B is cosine A cosine B plus sine of A sine of B. So I already proved this in my earlier, you can check it out. Thank you so much for watching.